Good morning, students. The topic for today is arithmetic circuits. So before going into the details of the arithmetic circuits, let's have a quick revision of what all circuits we studied in the previous lecture. I hope you are able to identify these two circuits that we have discussed intensively yesterday in our video lecture. Let's see the first circuit. Could you identify what circuit is this? Yes, this is of course an op-amp with feedback. Even the second circuit is also an op-amp with feedback. But let's see what are the inputs to it. So in the first circuit, the input is given to the inverting terminal. So this one would be the inverting amplifier with feedback. And in the second circuit, the input is given to the non-inverting terminal. So this becomes the non-inverting amplifier with feedback. So based on the circuits of inverting amplifier with feedback and the non-inverting amplifier with feedback, we will be designing some arithmetic circuits. Let's see what all arithmetic operations we are supposed to study in our syllabus. So the first circuit is an adder circuit or simply an adder amplifier which does the operation of addition. And the second one is a subtractor circuit or a subtractor amplifier which is doing the operation of subtraction. Now, what is an adder amplifier? The definition: an adder amplifier is an electronic circuit that produces an output which is equal to the sum of the applied inputs. An op-amp based adder produces an output equal to the sum of the input voltages applied at its inverting terminal. So, which terminal we use as the input? We use the inverting terminal to give the signals. It is also called as a summing amplifier. Either you call it as an adder amplifier or a summing amplifier. Generally, we use the term summing amplifier since the output is an amplified one. So this is a circuit of a summing amplifier. Let's just analyze this circuit. It is very similar to the inverting amplifier feedback, right? Because the input we are giving to the inverting terminal, since we have a summing amplifier, we have to give at least two inputs which can be added. So the two inputs are V1 and V2. If two inputs were not there, we were only calling this as R1. And the feedback resistor was RF. There is no input given to the non-inverting terminal. So this configuration is actually an inverting input with the feedback, right? So the above circuit, non-inverting input terminal of the op-amp is connected to the ground. Yes, it is connected to the ground over here. That means 0 volt is applied to the non-inverting input terminal. So let's apply the virtual ground concept or the virtual short concept. What was that? It says that whatever voltage is applied over here, the same voltage would appear at the inverting terminal. This we have discussed yesterday in our lecture. According to the virtual short concept, the voltage at the inverting input terminal of the op-amp is the same as the voltage at the non-inverting input terminal. So what is the voltage at the non-inverting input terminal? It is ground or 0. The same voltage will appear at the inverting terminal also. Okay. So the voltage at the inverting input terminal of the op-amp will be 0 volts because it is grounded. Now let's derive the nodal equation for this input terminal. We have done this yesterday. Let's do it step by step again today. It's an extension of the previous study that we were having only one input. Now today we have got two inputs over here. Let's see how it is done. So the nodal voltage over here is 0. And why is it 0 over here? Because of the virtual short concept, which is ground. So 0 minus V1 divided by R1 will be the current which goes through this resistor, right? Similarly, can you tell me what will be the current through R2? Yes, it would be 0 minus V2 divided by R2. Okay, so that's the second current. Then can you tell me what will be the current through RF? Yes, this is 0 minus V out divided by the resistor RF. So that will be the third current, and the sum of all these currents would be equal to 0 because there is no current flowing into the op-amp. So this is the nodal equation for the inverting input terminal. Okay. If we simplify this further, removing all the zeros, we get V1 by R1 minus V2 by R2 is equal to V0 by RF. And again, taking all the terms on one side, that is V0 on one side and RF on the other side, we get V1 by R1 plus V2 by R2. Okay. If all the resistors are assumed to be equal to R, that is R1, R2 and RF equal to R, then what will be the change in the output voltage? We can simply write them as minus R into V1 by R plus V2 by R. So in the denominator also we have R and in the numerator also we have R. These R can be cancelled. So ultimately what do we get? We get the output voltage is equal to minus of V1 plus V2. Now, so let's pay attention to the terms in the bracket. It is the summation of V1 with V2. Outside there's a negative sign. The meaning of this negative sign is that there's a phase difference between the input and the output. This is the case of the inverting amplifier used as a summer. So therefore the op-amp based adder circuit discussed here will produce a sum of the two inputs voltages, that is V1 and V2, as the output when all the resistors present in the circuit are of the same value. Remember that in this circuit we have assumed that the resistor values are all the same and that is equal to R. And also the output voltage V0 of the adder circuit would have a negative sign. This negative sign indicates that there is a phase difference of 180 degree between the input and the output. Now let's move on to the next topic, that is a subtractor amplifier. So the definition of a subtractor amplifier is that it is an electronic circuit that produces an output which is equal to the difference of the applied inputs. The difference means again we'll have to take at least two inputs. For this case we would assume two inputs. An op-amp based subtractor produces an output which is equal to the difference of the input voltages applied at its inverting and non-inverting terminals. We have to make use of both the terminals over here. In the previous case, in the case of an adder amplifier, we had used only one of the terminals, but here we would be using both the inverting terminal and the non-inverting terminals. So this is also called as a difference amplifier. So either you can call it as a subtractor amplifier or as a difference amplifier, since the output is an amplified one. This is the circuit of a subtractor amplifier. Now just have a look at it. There is RF, that is the feedback resistor. There is R1 as usual we have. Then at the non-inverting terminal there is R2, which is the bias resistor, and there's also one more resistor which is connected to the ground. Okay, so there's R1, R2 and R3 at the inputs. The voltages that we are giving is V1 at the non-inverting terminal and V2 at the inverting terminal. The output is measured as V0. Okay. Now let us find the expression for the output voltage of the above circuit using superposition theorem. I'll tell you what is the superposition theorem in step by step. This is the circuit in which I have shown the previous slide. So there is V2, there is V1 and there is V out. Okay. Now what does the superposition theorem says that? It says that in step 1, okay, we have to consider only one of the inputs, that is V1, and then with respect to this V1 you find out what is the output voltage V out. That's step 1. In step 2, what we do is we take the second voltage, that is V2, and then you find out what is the output V02. So that is step 2. In step 3, what we do is whatever output voltages we have got in step 1 because of V1 and in step 2 because of V2, these two have to be summed up. So in this step, we will obtain the output voltage V0 of the subtractor circuit by adding the output voltages obtained in step 1 and step 2. It's relatively easy. Let's go and see how the circuit is analyzed. Firstly, let us calculate the output voltage V01 by considering only the input V1. So V1 is over here and V2 is over here. We are going to consider only the input V1. V2 has to be removed, or what we do is we make it as a short circuit and we get the modified circuit diagram which looks something like this. So difference between this circuit and this circuit is that the input V2 has been grounded. This is step 1. Now let's analyze the circuit using voltage division principle. See, this voltage division principle we've explained yesterday how it is done. If you assume that the voltage is Vp over here, okay, and V1 is the voltage over here, then if two resistors are in parallel, to find out Vp, what we do is we do R3 divided by the sum of these two resistors. Okay, yesterday we did it with the help of R1 and RF in the previous lecture. Today we have to do it with respect to R3 and R2. So Vp is equal to R3 divided by R2 plus R3 into the input voltage, that is V1. So that is the nodal voltage over here, that is Vp. Now the above circuit is just like a non-inverting amplifier having the input voltage as Vp, and therefore what will be the output voltage? V01. We have done this yesterday. The input voltage, if it is Vi, then the output voltage will be equal to 1 plus Rf by R1 into the input voltage, that is Vp. Okay. Once again, I'll tell you. For the first step, what we have done is we consider only input V1, we ground V2, okay, and then we apply the voltage division principle where we find out what is Vp. This Vp is equal to the input voltage into R3 divided by the sum of R2 and R3. And this configuration is nothing but the non-inverting amplifier where the input is Vp. For that, the output voltage equation is input voltage into 1 plus R1 by Rf. So input voltage is Vp. That is what we have written over here. Okay. Now let's go to the next slide. That is substituting the value of Vp over here. Now what is Vp? It is nothing but V1 into R3 by R1 plus R2. So once you substitute that in the equation, you get this as the final value for V01, and V01 is the output when only input number 1 was considered. Next, step 2, same way we remove V1 and we consider only V2. So what will happen? We'll get a modified circuit diagram, and that would look something like this. See, there is no V1 over here, only V2 is there. This one is very easy to do. How? Because this becomes an inverting amplifier with feedback. So what is the output of the inverting amplifier with feedback? It is nothing but the input voltage into minus of Rf by R1. This I have told yesterday in the previous lecture. So your output voltage will be equal to V02. Okay, why is V02? V02 is nothing but the output voltage when only input at terminal 2 was considered, minus Rf by R1 into V2. Okay. In step 3, what we do? In step 3, we add the two outputs, what we have got as V01 and V02. So mathematically, this would be V0 is equal to V01 plus V02. The values of V01 was this, the value of V02 was over here. Now you add these two, what do we get? We get this complete equation. And then again, we have to make some changes in the equation, that is rearranging it. And also we can assume here also that Rf equal to R1 equal to R2 is equal to R. So putting all these resistances value as R, the entire equation for V0 will change to this. Now you can see there are a lot of common terms which can be cancelled. This R will get cancelled. Here also there will be cancellation. Here in the numerator there is 1 R, in the denominator there is 2 R. So you solve that entire equation and you get V0 to be equal to V1 minus V2. Now we were studying about a subtractor circuit. Essentially, what's a subtractor circuit? It's supposed to give you the difference of the two inputs, and the two inputs over here were V1 and V2. So the op-amp based subtractor circuit discussed above will produce the output, which is the difference of the two input voltages V1 and V2 when the resistors are of the same value. Again, we assume over here that the three resistors actually, that is R1, R2, R3 and the feedback resistor, all are having the value as R. Okay. So with that we come to the end of today's discussion. Thank you.